Okay, example 3, growth of bacterial. The number of bacterial n in a petri dish after t days can be modeled by the exponential equation n equals to n0 a power t. Okay, where n0 and a are constants. Okay, find the initial number of bacteria is 17. Find the value of n0. Okay, so n is equals to n0 at, right? So initial number of bacteria is 17. That means when t is equals to 0, okay, your n is equals to 17. So you sub in, so 17 equals to n0, a power 0. Okay, a power 0 is 1, so n0 is 17. Okay, easily done. Now, after 2 days, there are 68 bacterial. Calculate the value of a. That means when t is equals to 2, n is equals to 68. So 68 is equals to 17a square. Right, a square is equals to 68 over 17. So a is square root, which is 4. Okay, so square root of 4, which is plus and minus 2. Then you got to ask yourself, because the question says calculate the value of a, so you have to ask yourself whether you can accept negative 2. So you can't accept negative 2, because if your a here is negative 2, then it will be positive when t is even and negative when t is odd. So you can't have the number of bacteria being negative. Okay, so you have to therefore reject negative 2. So therefore a is 2. Okay, clear? Alright, then part 3. Okay, part 3. Given that the number of bacteria exceeds 300 after k days, where k is an integer, a whole number. Okay, find the value of k. Okay, so in this case, part 3, this is an important part now. Part 3. Okay, given that the bacteria exceeds 300, so number of bacterial is definitely more than 300. Okay, so how many days you would need for it to exceed 300? Okay, so 17, okay, your equation, n is 17, 2, right, a is 2, to the power of t. T in this case is k number of days, right? So more than 300. Okay, so this one is 2 power k is more than 300 over 17. Okay, then again, you have your exponential equation. Okay, so Lg 2 power k is more than Lg 300 over 17. Bring this to the front. So k Lg2 more than Lg 300 over 17. So k is more than Lg 300 over 17 over Lg2. Okay, so that is 4.1413. Sorry about that. Okay, so they say that k has to be an integer, right? Whole number. So k must be 5 days. Okay, k number of days. So k is 5. Yeah? Alright. So easily done. Okay. Part 4. Predict the number of bacteria after 6 days. Okay, after 6 days. So t equals to 6, right? So the number of bacteria will be 17 times 2 power 6. It's about 1088. Okay. So, and then the last part, after 6 days, the number of bacteria is found to be only 986. Okay, I'm not too sure how they actually can count the number of bacteria, but anyway, okay, so after 6 days, the number of bacteria is found to be only 986. So just 2 reasons why the actual number of bacteria is different from the number predicted by the equation. Okay, so just 2 reasons. Okay, one reason could be what? There is error in the data collection. Okay, so it could be, so there's one reason possible. Okay, error in data collection. Okay, B, right? Perhaps, they didn't start with that number. Okay, right? What about second reason? Second reason it could also be because you use the model that you use is this, you see, class. You assume that it follows this model. Okay, you assume that it follows this model where n0 is 17. Okay, so your model is n is equals to 17, right? A is what? A is 2 power t. So you assume that your bacterial growth follows this exponential graph, but it may not be so, you see. And why is it in real life it may not be so? Because you cannot expect bacteria to grow exponentially for forever. Okay, up to some point it will slow down. Okay, right? So the second reason would be, okay, the growth of bacterial actually slowed down. Okay, so the curve, okay, is not an exact model of the growth. Okay, right? So up to a certain point, okay, it actually grow differently, okay, from what is predicted in the curve. Initially, maybe in the earlier stages, earlier few days, is accurate, but after a certain number of days, it deviates from this model. Okay, right?